Okay, great. Well, welcome everyone. We're really excited to see you, and we're looking very forward to Professor Saeed's presentation and the 20 minutes of Q&A session that will follow. This seminar series is part of the Transboundary Groundwater Resiliency Research Network, which is an NSF-funded project that connects hydrology, social science, system science, and data science to advance water research. We have just a few announcements. So if you're not already part of our mailing list, we encourage you to sign up so that you can stay up to date on the network's most current research and collaborative opportunities. And we also encourage you to join our newly launched Slack channel to keep the conversation going after today's presentation. TGRR also has volunteer opportunities available for students and early career researchers. And as you see, we're putting the links in the chat for the mailing list sign up, volunteer sign up, and Slack channel. And with that, I'm going to pass it off to TGRR PI and Director of the New Mexico Water Resources Research Institute, Dr. Sam Fernald, to introduce Dr. Saeed.
Wonderful. I'm going to just give a brief intro. Dr. Saeed's from Worcester Polytechnic Institute, which is really well known for system dynamics, and he is a professor of economics and system dynamics there, widely recognized for work on the interface between economics and system dynamics, and admittedly not well versed in hydrology, but we're so excited because system dynamics is such a useful tool for water topics. He's published 2 books, numerous articles on various methodological development and management topics, including sustainable agriculture, poverty alleviation, political instability, supply chain management, and system dynamics modeling, and now focuses on operationalization of economic policy for implementation through managerial roles. And I think with that, we greatly look forward to your talk, Dr. Saeed.
Thank you. I'll begin by saying that I'm greatly honored to talk to this audience. As you mentioned, a disclaimer that I'm not a hydrologist, but I have scratched on the surface. I work on a variety of issues. More recently, I've been working on money, and I do see some similarities between money and water, which I'll allude to later. Kristen asked me to weave in a few thoughts on system dynamics with the subjects, and I welcome that opportunity because primarily I work on system dynamics. So I'll also throw in some thoughts on money because that's the recent subject I've been working with. I just published an article on taxation of fiat money, which I think something that has been ignored, but that's another subject. Now, as I said, I feel water and money are very similar in nature, homogeneous, measurable, and conserved in a system of reservoirs and flows. No wonder hydrologists use the term budget also when talking about watersheds and town water and wastewater systems. And the analog computers mimicked stocks and flows. Even an early model of an economic system, which was built by Professor Phillips a long time ago, it still is preserved in possibly a museum in UK. It really consisted of reservoirs and flows and mimicked the flow of water through this system to represent a macroeconomic system out there. I can definitely relate to the budget analogy in money, which is used by my hydrology colleagues here, and is the keyword budget is part of the topic that I have selected for this talk. So we will talk about watersheds and budgets. And since the building block of system dynamics model are similar, I'll sort of talk a bit also about system dynamics in the process and how it differs from using calculus for modeling, although I'm sure a lot of hydrologists use calculus differential equations for modeling the reservoirs and flows. Now, stocks and flows are indeed like bathtubs, as Christine mentioned in the beginning, drains and faucets. But we explain the simulated behavior of the stock flow system using feedback loops. So we do not create a general solution. We try to articulate our understanding using the feedback loops. In early writings of system dynamics, in fact, feedback loops were not explicitly mentioned. And here's a challenge. If you folks have seen Forrester's Industrial Dynamics, which was published in 1950s, check it out and see if you can find any feedback loop in it. Actually, there are none. So feedback loops, explicit representation of it came later, although in the descriptions, they did appear in the early writings as a part of the explanatory process. Currently, system dynamics uses both stock flow diagrams and feedback loops. It can represent the accounting process in any system using stock flows. And by any system, I mean including engineering, economics, social organizations, and whatever exists out there. Now, modeling a system, however, has been different. Stock and flow representation is very intuitive, but modeling it has been in another domain. Here are generic accounting systems for water and money. We keep track of money using income, expenditure, and a balance that builds up when the two are integrated. Similarly, we can keep track of water in a bathtub by keeping track of inflow through the faucet and outflow through the drain. So as I said, so far so good, very intuitive. But when it comes to modeling these systems, this is what we have done. We have unfortunately abandoned the intuitive stock flow analogy and adopted the abstract protocol of differential equations. I think because the intuitive route involved oodles of tedious computations. Thus, the rate of change of balance is equal to income minus expenditures. That's the differential equation. You integrate both sides, you get balance equal to balance at time 0 plus income minus expenditure multiplied by T. Now, for models with autonomously determined flows, a calculus solution still looks quite intuitive. However, when calculation of flows involves feedback, calculus solutions, though magical, are hard to understand and give no clue about where the feedback is, by the way. Let me start with an example here. This is a very simple differential equation representing the growth of population. So the rate of change of population is equal to population multiplied by birth fraction minus death fraction. And if you integrate both sides, you get the solution. Population at any point in time, t, is an integral of whatever was on the right-hand side. And if you solve this integral, the solution is P0, population at starting point, multiplied by e to the power birth fraction minus death fraction multiplied by t. Now, if you look at this solution, it's very elegant. It can give us the population at any point in time. And if you know what E is, you might also get some idea about the shape of growth, that it would be either exponential or no change, exponential growth or exponential decline or no change. But you have to know what this element E is. To a common person, this equation might mean nothing. It's certainly not intuitive. There are no variables on right-hand side, and it gives no clues about where the feedback is. Now, we have adopted this type of representation also in water. I just want to add that. Now, I talked to Forrester, and I assume everybody knows Forrester. He invented random access memory. He built the first computing system, Whirlwind, which filled a whole floor in building E40 at MIT. He was a control engineer. He knew his calculus. He also, as I said, built computer systems, etc. He then turned against calculus and devised an intuitive stock flow representation of differential equations. Now, this excerpt that you see on the slide is from a fireside chat that I conducted with Forrester in 2013. And he says one thing we should look forward to is a replacement of differential equations in engineering and social sciences. Differential equations have been the fundamental way of dealing with dynamics. It is terribly misleading. It causes a great deal of harm. It's not me, that's Jay saying. And I'll not comment on it. We'll go to the next slide and try to resolve this comment. Towards the end of my conversation with Jay in this chat, I asked him, hey, Jay, what would you like to be known for in about 20 years? And this is what he said. I'd like to be known for having thrown out differential equations in all fields. This is not going to be over the next 50 years. I would like to be known for having completely replaced economics. And that's not going to be in 25 years either. There are a few other things, but that's enough for now. And I think this comment was very thought-provoking. It got me working on what I have started calling operational economics, because I'm beginning to understand what he meant by replacing economics, and also beginning to understand what he meant by replacing calculus. And we'll talk a little bit about this. Things that you might already know, but might be worth going over. So let's start with a differential equation that population representation, and I'm changing the term dp by what it is. It's a small incremental change. So dp, I've replaced dp by the value at time t minus the value a moment ago, which is dt ago, divided by tt. Dt is equal to whatever the right-hand side was. And then I've rearranged terms, and I've ended up with this equation at the bottom, which says population at time t is equal to population a moment ago plus births and minus deaths over that moment. Now, this is very intuitive. This is like the bathtub and faucet and drain. And he actually wanted calculus to be replaced by this intuitive process. It was difficult to do so because this intuitive process, implementation of this intuitive process is very tedious. You have to have someone calculating these things over small increments and then adding and subtracting them. And when calculus was used, it actually sidetracked all this tedious process and presented with a magical way of getting to the solution. Now, with the invention of computers, the tedious part is now done by computers. We don't have to do that tedious part. So the question is, why not replace the differential equations with the intuitive logic that underlies those differential equations? I think one of Forrester's important contribution is this transformation. And in those times, we didn't have graphical interface to creating these representations, but he did create the icons, which we still use. And these icons are stocks, flows, and converters are actually intermediate calculations. And then we have graphical functions, which are like submodels with small time constants that we can insert in instead of the stock and flow structure. And there are information links. A few technical things why the converter and the graphical functions were introduced. Both converters and graphical functions are instantaneous calculations. So in terms of the time constant of the systems in the model, the time constants of these computations are very small. So actually all computations have a time constant, but if you combine very large and very small time constants in a system, those of you who have dealt with numerical integration know that we create stiffness. And stiffness leads to integration errors. So these simplifications have some technical reasoning behind them. In theory, the two building blocks of systems, computational building blocks, are only stocks and flows. Because we represent very short time constant computations, we can use converters to represent them. And then sometimes we represent these short time constant relationships by submodels, which are graphical relationships between two variables. Those can also be very viscerally represented using a graph in our software. But although this software did not exist at that time, these icons existed, and we had to draw our model using these icons first, and then program them using Dynamo, which was the more evolved version of simple that originally was created by Forrester's co-workers. Now, switching from here to water, all watersheds or waterfall systems consists of conserved stocks and flows. So in fact, it's not a single stock, it's a system of many connected stocks in which the flows are conserved. They often do not come from clouds and go into clouds as we uh, show them in a single stock, but might go into other stocks and other flows. When this conservation process is outside of our system boundary, only then we use stocks. All right. And the examples are there's municipal water supply, but there are other examples also of having conserved systems consisting of multiple stocks connected together. A very well-known uh, archetype is rework cycle, which is very widely used in project management. It's also a system of connected stocks. Economic institutions and sectors are usually connected stocks. Mobility-driven workforce chains. There are several types of workers. Forrester represents them, for example, in urban dynamics as managers, underemployed workers, and regular workers. And because of the mobility, they can move from one stock to the other. I would think that Schumpeter, before Forrester, represented them as entrepreneurs, workers, and workers, and the mobility between them. Now, there are others I've mentioned here. There is allocation of effort to production and other organizational tasks in an organization where same type of people handle production and sales. Your time can be allocated between production and sales. I remember as a student, I worked with a company who called Development Analysis Associates. This was an MIT spin-off. And these were all very well-versed system dynamicists and operational research people and hydrologists. And in my first interview with them, they said, you know, we are very busy with implementing a very large project that we have. And we know that we are neglecting the sales effort, the developmental effort, and we are hiring you to develop some new research proposals. We'll try not to absorb you in our mainstream effort, but what happened actually was that after a few months, they said, hey, Khalid, we are a bit short-handed. Can you come and help us with our model that we're developing for the client? And my sales effort, my new development effort was abandoned, and I moved to the production side. So there's mobility between the workforce, and these are connected stocks. There is the chronic disease propagation process. There is the infectious disease propagation process, new product adoption process. All these work on the principle of several stocks connected together into a conserved system. Now, as far as the watersheds are concerned, the questions which were formulated by my hydrologist colleagues are here. First of all, the concerns are that in this system of connected stocks, there are high flows and low flows, and also there are quality issues. And the questions were that what are the controls and how effective they are? How can we address emerging concerns? And how can we make decisions to manage water and stormwater effectively? And let me mention my colleague's name. Professor Paul Matheson works in the Civil and Environmental Engineering at WPI. So we start talking about creating a very simple model that could be experimented with for managing for managing town water, town sewer supply systems. And we started with a more complex framework, but ended up with a simple one. So let me show you that simple framework and let me try to explain what is it. So you see three stocks in this system. There is the groundwater, there's the municipal storage, and there is the surface water in rivers and lakes. Now, groundwater in aquifers increases through infiltration, and the infiltration can come from storms, from say rainfall. It also can come from septic. These are two types of infiltration. And also there is some infiltration from seepage from surface storage. So there is a surface storage, seepage from it creates some infiltration, all goes into groundwater. And if groundwater is extracted either by the homeowners or by the municipal organization into their reservoir, it goes into this storage, and I've not made any distinction between the homeowner storage and municipal storage. So it goes into this aggregate storage. And water use comes out of this storage. Additionally, in many towns, there is intake from surface water in rivers and lakes. In particular, in New England area, we have a lot of lakes, and there is intake from those lakes, which goes into the municipal storage here, which is then extracted and used. All right, so pumping for the town mainly is done out of this municipal storage. Municipal storage is filled either by extraction through groundwater or intake from surface water channels. Another system out there is the treatment. Now, some houses have their own septic, and they are not connected to the town septic system. Others in better towns, all towns want to have their own septic. So there is town water, town sewer system. So when the sewer water is treated by a centralized septic system, its effluent its impurities are removed, but then the water is discharged usually into rivers and lakes. So it really adds to the surface water system. On the other hand, if town sewer does not exist and the homes have their own sewer, the water from that sewer is dispersed into the ground, and it actually seeps into the ground aquifer. So it adds to the infiltration. The homeowner controlled septics add to the infiltration. The town run septic adds to the surface water and rivers. So it flows out of the system into the sea. So this is a very, very simple model of the system. Now, let me pause this PowerPoint for a moment, and I see that I'm running to, I have some 8 minutes left, but I think in those 8 minutes, we can perform some experiments with this very simple model. Can you still see my screen? Now the screen has a control panel on it to experiment with. All right. So this is the model, and this is the control panel through which you can experiment with the model. Those of you who have used Stella must be familiar with it. There is a layer in which you can experiment with the model that you construct. So I'm going to use that layer for this experimentation. And I have created all these sliders in various domains. Municipal water supply programs, in fact, can change policies which can either increase or decrease intake from the surface bodies, or can change the extraction rate from ground, or can change the pumping rate. If a town decides to pump more water, it can change pumping rate. Wastewater policy is the really translates into building bigger and better wastewater treatment systems, which means that you increase the fraction of wastewater that is treated. Infrastructure policy means building more infrastructure. Now, I moved to this town that I live in 20 years ago, and over this period, the town has built new market areas, new housing areas. So they built a lot of infrastructure. And infrastructure building actually decreases the stormwater infiltration because, well, there is all that concrete that's laid out and there is less room for the water to infiltrate. And climate change can cause changes in the stormwater runoff over our lifetime. Probably this will change. This has not changed very much. But I want to demonstrate that this simple model allows us to manipulate several policy levers here and see how the system will work. Now, a lot of time, there's an effort to calibrate a model so that it recreates history. Personally, I prefer calibrating a model so that there's a hypothetical equilibrium, so that you can change a policy and see how that equilibrium is disturbed. So for this model also, I created a hypothetical equilibrium. If you run this model, sorry, it should be in run mode here. Run this model, everything is in equilibrium. Groundwater is in equilibrium, municipal storage is in equilibrium, and water use in equilibrium too. Now we can change these policy levers. For example, if we increase the intake from rivers and lakes, say, like so, it seems that we can increase the municipal water storage. We just increase the intake. We did not increase pumping. If at the same time we are able to supply more water to the residents in the town, the residents have more water, but municipal storage is the same. If we change the pumping even more, the reservoir will decline. However, groundwater really does not change because we are not increasing any extraction from groundwater. So let me change this back here. And if we increase the intake from groundwater, say more residents build their own tube wells and you increase the intake from groundwater like so. Here it's assuming that you extract more water from ground and store it. So the storage is going up. However, and of course the water use depends on storage, that goes up a little bit also. But if you increase pumping also, then you have, sorry, I should change. This was the extraction. Let me change it back, change back everything. Let me increase the extraction rate. And at the same time, first of all, you notice that the groundwater in aquifers is going down when you increase the extraction rate. If you increase also pumping, households have more water and municipal storage is down, and so is the groundwater. If you build more infrastructure, which all towns aspire to build, then the treated fraction, sorry, wrong policy lever here. This is the infrastructure. If you build more infrastructure, the infiltration fraction goes down and the groundwater declines, right? If you treat more wastewater, that means you have municipal sewer system. Again, the infiltration declines because you are pumping a larger fraction of wastewater to the streams, which take it to the sea and does not infiltrate into the ground. So our idea was that this simple model can help towns to formulate a policy. Like in the summers, we are told not to water our lawns, although watering our lawns also means that we will increase infiltration because a good part of the water we use to irrigate our lawns infiltrates into the ground. Perhaps a policy of centralized sewer system is not a great policy. The policy of developing the town, like the town I live in, is far more developed than it used to be some 20 years ago when I moved in. Is that a good policy? So there are all these questions that you can address using this simple model. I have to admit that I did not do much with this model, but my colleague Paul probably has involved more students into it, and I do see some student projects being conducted using system dynamics. I want to show that even a very simple model can create policy insights. So I want to briefly talk about the multi-stock systems that I alluded to in the beginning. These are based on water analogy, and in system dynamics, we refer to them in two ways. There are the aging chains and there are the watersheds. So aging chains are like population, infrastructure, students and faculty in a school, rookies and experienced workers in professions. And watersheds are the municipal water supply and wastewater disposal system that we just discussed. There's a rework cycle, economic institutions and sectors, mobility-driven workforce chains, allocation of effort to production and other organizational tasks, chronic disease propagation and infectious disease propagation, new product adoption. And I just want to very briefly show you how these systems might look like. Aging chains can appear in population cohorts, infrastructure, students and faculty, and professional workforce, as I pointed out. And there is some difference in how we represent them. A demographer would represent an aging age pyramid like this. A system dynamicist would represent in terms of these three stocks, which are very similar to how water works. I'm rushing through it a little bit, but well, please bear with me. Infrastructure construction, you start with planning, and then there are things under construction, and then there are commissioned and in use. And then there is a demand, and the shortage drives more planning. So this is the connected system. Then there is the information links, which drive the decision process. I've taken more infrastructure examples from urban dynamics. The construction of businesses, start with a new enterprise. After some aging, it's a mature business and then transforms into declining industry. Likewise in housing. Now, an interesting thing is that when you have a system of connected stocks, you can create multiple equilibria. In equilibrium, more units can be in this stock, less in this stock, and less in this stock, or there can be more units in this stock, less in this stock, and less in this stock. And we do see in organizations and economies systems which are somewhat different. Like if there is more declining industry and few new enterprises, a city would look run down. If there is more underemployed housing and few premium housing, city would look run down. On the other hand, if there are more units in those stocks and fewer units in these stocks, the infrastructure would look much better. The place would look affluent. This diagram is taken from a project that we conducted for electric boat some time ago. And the engineers in electric boat were concerned about spending too much time and spending too much time in maintaining the quality. And in particular, we looked at the engineering design organization and the various categories of people which moved between those groups in this organization, and how this affected the quality control process. And again, you'd see that these are multiple stocks connected together, just like the ones that we saw in the water budget system. Production and marketing, I mentioned my personal experience of working with an organization that was concerned with keeping more people in the area that could promote the sales, but then the backlog forced moving my effort and my colleagues' effort into production. By the way, if I graduated in the fall of 1980, and in 1982, I visited Cambridge, Massachusetts again, and went to see my colleagues in this company, which at the time I left it consisted of something like 100 people. And now there were 2 people sitting in an office because while they had not taken care of the sales force, they have moved everybody into production. And when the pipeline went empty, that's what happened to the company. This is from some work that we did for Veterans Administration on chronic disease propagation. And again, you see a system of connected stocks like watershed. Here is some work we did for an organ transplant organization. And again, there are these connected stocks and conserved flows using the water analogy. And infectious disease propagation, this is a simple model I constructed for my class when COVID hit us. And again, you see a system of connected stocks. And let me stop here and come to the conclusion. Watersheds, my one important emphasis here is that watersheds create multiple equilibria. They come to balance with a variety of distributions of units among connected stocks. They have potential to create multiple dynamic equilibria that often manifest in the variety of economies, markets, and firms that we see around us. And these equilibria are often seen as static existing conditions, like we might refer to mass poverty, anarchy, feudalism, shortage of transplant organs, need for marketing. But these are all manifestations of dynamics which are happening in that system. So addressing just a snapshot of symptoms, in fact, can be very ineffective. And experience shows that it's been ineffective. Watershed analogy can help to visualize complex social and economic systems also, in addition to modeling water. So let me stop here for questions. I have some other stuff which is about relating the feedback process to the computational process, but that can wait.
If anyone has any questions for Professor Saeed, please feel free to unmute or use the chat.
I have a...
Yes, Sam.
That was a wonderful talk. Thank you. I'm just wondering, in watersheds, we have so many possible drivers because of the biophysical and socio-cultural factors that affect water flow and storage in surface water and groundwater. So I'm wondering if you could give us some of your experienced guidance on determining the bounds of our water models in the system dynamics framework.
Excellent question. Thank you. In fact, that would help me segue into describing the feedback process. I think what you're alluding to is that there are multiple systems. There are multiple conserved systems, and they're connected together through the feedback process. And I've not really touched on that part. I've seen a lot of time people try to create feedback loops that are mapped directly into the stock and flow system they have modeled. And sometimes they do that at a very aggregate level, but there is no systemic way to do this, although I think a systemic way was described by Forrester. It's just that we haven't followed it. So bear with me for a moment while I try to delineate the difference between feedback and stock and flow process. And then we can discuss how various conserved systems are connected through the feedback process. It's in that connection that we can find various policies. It'll be a connection between the water systems and other social and economic systems. And it's in that connected framework that we can identify policies that help us manage our hydrological processes in such a way that they create welfare for the populations that they serve. And also at the same time, there is sustainability. I think those are the challenges in connecting these various systems. So let me start with a very simple stock and flow model, again, that population growth, births, and deaths. Now, this is so simple that we see two feedback loops here. One feedback loop creating the growth, the other feedback loop creating the decline. But these are not really feedback loops, because feedback loops consist only of information connections. Here we have one information connection and one flow. So yeah, we can see with our mind's eye that there's a feedback, but this is not how feedback is represented. On the side of deaths, it's even worse. This arrow really goes in the opposite direction. And again, we have to surmise that, yeah, since it goes in the opposite direction, there's a causal link which is in this direction. So there's a feedback. It's a sloppy way to represent the feedback. The feedback in this system is really more population, more deaths, less population, more births, more population. No differentiation between stock and flow, and the information links are the same. This is how feedbacks should be represented. Now, if I decompose that stock and flow model into three computations, the first computation is the calculation of the births, which is population multiplied by fractional birth rate. The second computation is keeping track of population, which is the stock that's increased by the births and decreased by the deaths. The third calculation is the number of deaths, which is population multiplied by fractional death rate. So this completely describes all three computations. And I can enclose these three computations into separate modules. In fact, Forrester devised this term, which he called sectors. Even his earliest models were divided into sectors, in which he put in clusters of equations. So these are the three clusters which I put into sectors. And in Stella, now it's possible to have a hierarchy. So each sector is in a module, and in the upper layer, it would show how modules are connected. So if I create a model in Stella and put these computations into three modules and went to the upper layer, it will give me that feedback map that connects these computations. Now, I use a single conserved system to make this point, but we rarely use such separation of computations in a single conserved system. Usually, we connect various conserved systems, but this was to illustrate a point that feedback is a different beast. It's a different model. It's a mental model. It's qualitative. It consists only of aggregate variables. And aggregate variables in our various conserved systems is that whole conserved system. And several conserved systems connected together, in fact, would be connected together through feedback process. And it's interesting, there's a very well-known paper by Forrester, which he published back in 1950s. You might have, I don't know if people have seen it. It's called Market Growth as Influenced by Capital Investment. And this diagram is taken from that paper, in which he creates these sausages, and each of these sausages is a sector. He divides his equation clusters into sectors. So this is a sector, this is a sector, this is a sector, and this is a sector. And then he connects these sectors through these links. So this creates one loop. This creates another feedback loop. This creates another feedback loop. So just for fun, I took his equations and I put them into these 4 clusters using Stella. And I put these in modules in Stella, and I ended up with this map. And if you compare it with the sausage map that Forrester presented, this is exactly the same. Here is the salesman sector. Here is the production sector, production planning. Sorry, this is the orders book sector, production planning and capacity expansion. Salesman, order backlog, so delivery delay, and capacity expansion. So even though he did not have this software facility available to him, that's how he visualized the system. That at the computational level, there are these conserved systems. And I demonstrated a conserved system in case of water. Now, the other conserved system may not be water. It might be some other social, technical aspect. And I tried to use the water analogy to define some other systems. Let me go back. Multi-stock systems. So we can have a multi-stock system which pertains to water, other multi-stock systems which pertain to economic institutions, other multi-stock system pertaining to population, and they get connected in this way. And once we understand the feedback which drives them, we can experiment with these systems to devise policies for sustainability and also for delivering best value to the populations that they serve. I hope I addressed your question, Sam.
That was a very nice answer. Thank you.
Thank you. We are at time now. I'd like to thank Professor Saeed for presenting, and thank you for attending this presentation.
Thank you, my pleasure.